My name is Seuntgens, by the way. I'm from McGill University. So much of what we will say will be handled or has been handled in a recent AAPM summer school. And I strongly encourage you to, if you don't have this already, to purchase this book, because it is a very extensive compendium of principles and applications nicely put together in one piece of work with questions and answers, and as I said, nicely built up to consist of one piece of work. I already explained this, 3 parts in the session. In my part, the first part 1, I will discuss a few background issues, some definitions and nomenclature. I will discuss some fundamental issues in non-standard beam dosimetry, and we will look at the new formalism in some detail and an example. So, you know that developments in radiotherapy technique have moved towards the use of small fields or large uniform fields consisting of a multitude of small fields. And this has been accomplished by using beam modifiers such as MLCs, micro MLCs, and this has become common equipment on accelerators. The radiotherapy procedures have become much more developed in the sense of novel dedicated treatments using, for example, tomotherapy, cyber knife, or gamma knife, or IMRT treatments that are carried out on traditional accelerators, such as rapid arc or VMAT, such techniques. So here are some of the hardware for tomotherapy, cyber knife, and the machines that deliver VMAT and rapid arc. Dosimetrically, what can we do with these machines, or how do we calibrate them? The standard accelerators can realize the standard reference field that is recommended in operating procedures such as, or code of practice such as TG51 and TRS-398. But they also have, obviously, they operate mostly in clinical mode under dynamic delivery mode. Tomotherapy, cyber knife, gamma knife, there's no option for them to deliver in 10 by 10 conditions. And so the kind of the fields that are close or relatively close to 10 by 10, or as close as possible as the machine can realize, are listed here, and it's far away from 10 by 10 fields, obviously. And all these all these pieces of hardware can deliver in step and shoot or dynamic mode. So what are the issues with this? There's no primary standards for these beams, so that's one problem that the community should be worried about, because if there's no primary standards, then ultimately there's a break in the chain for traceability. Delivery protocols in non-standard beams, they are not standardized, so we could, if you think about protocols that would allow you to calibrate in non-standard beams, they are not existent, basically. And what is currently happening is that for the devices that can realize 10 by 10, the connection between the 10 by 10 field and the delivery conditions is made basically by the treatment planning dose calculation algorithm, and so that introduces some uncertainties. Here's an example of a raw comparison of clinics that have a Novalis system and that were asked to just measure output factor as they saw fit, without specific recommendations on how to do so. And so there's 2 fields involved here, 18 millimeter and 6 millimeter fields. And this is sort of a histogram of the results that the Brainlab company received. So there's about a factor of 2 in dose determination for the small field, showing the need for some guidance in how to do these kind of measurements. Some definitions and nomenclature and some jargon that gets used in this area more frequently with increasing frequency. So one can talk about a broad field in which case we have lateral charge particle equilibrium, a narrow field. In this kind of conditions, one would have problems with achieving lateral charge particle equilibrium, and a small field is defined as a field with size smaller than the lateral range of charge particles. So what are non-standard fields? These can be either small or composite. Both of them you can call non-standard. Single small fields can, in which case charge particle equilibrium is not present, or composed field, in which case we don't know. It could be that charge particle equilibrium is present, but it could also be not the case, and it depends on what kind of deliveries you provoke. Why? Just a brief few words about why is this a worry in dosimetry. Well, if you look at conversion of dosimeter signal to dose to the medium, one has to look at the mechanisms, the different mechanisms that are involved with different kinds of dosimeters. I'm not going to go through the list, but for example, in gas-filled ionization chamber, one has ionization in gases, and there's a path for conversion to dose to the medium. And basically, this is a simplified version of a more general treatment that I would refer you to the book that I pointed out earlier. One basically has a reading of a dosimeter and some kind of factor that converts the dosimeter reading into the dose to the dosimeter medium, and then there is a dosimetric dose conversion coefficient that converts average dose to the detector into average dose into dose to the medium at a point. And so the challenge is to determine, in fact, both these factors. The C factors has to do with fundamental physics. We cannot calculate it easily. The F factor is clearly a dosimetric question, and it's this F factor that deserves attention when you talk about non-standard beams. Just a table to illustrate for different techniques what these factors become. For example, for a calorimeter, the M would be a temperature rise, the C would be the specific heat capacity, and there would be no conversion. For chamber, you would have the charge. You convert it to dose to the medium with this factor, involving the average energy to produce an ion pair and the mass of the gas, and then you have the stopping power ratio and the perturbation corrections. Now, why do we worry again about charge particle equilibrium? Well, if you have specifically this quantity related to in ion chamber dosimetry, the stopping power ratio, you need the electron spectrum, and for the so-called Spencer-Attucks cavity theory, this is the way this was assumed, is that you have the spectrum in the unperturbed medium. Of course, when you insert a dosimeter, you don't have an unperturbed spectrum, and so whereas you can calculate this quantity theoretically, the representation of this stopping power ratio as a dose ratio is not very accurate, or can be not accurate. And so one has to worry about these extra correction factors that fix up the stopping power ratio to get to a proper dose ratio, and specifically in areas where charge particle equilibrium is not present. This is an example, stopping power ratio for a very narrow field, an extreme example, admittedly, a fairly small chamber to measure this field, and what is shown here is the ratio of dose to water to dose to the air volume, and you see that this varies by about 60% between off-axis and in the field, and the stopping power ratio would predict none of this, obviously. So these factors, they are traditionally factorized into wall, gradient, central electrode, fluence, perturbation, correction factors, and they are also dependent on the field size, the radiation quality, and so on. And they can be very significant in non-equilibrium conditions. IMRT is far from standard conditions, and nonetheless, if you calculate that stopping power ratio, you see that it does not vary very much compared to an open field in this case, this IMRT field. And this is because of the spectrum, really, of that composed field is not very different. Now, what does that tell us about dosimetry? I have again listed a number of extreme fields. These are static fields here, and the lower portion, starting from G, are dynamic fields. And Hugo Bouchard just finished a paper which is in print in Medical Physics that calculates all the factors in detail for these two chambers in these extreme fields. And this is just a snapshot showing the components of the replacement correction. And you can see in the original field here, this is a static field, you expect extreme effects. But also in the dynamic fields here, which are used for IMRT, these factors are potentially very large. So obviously, you would never in a clinic use a single field to do an IMRT dose measurement in. You would use the composed field. So we have to come back to that. And that's shown here where there's a typical QA measurement, maybe not so typical, but a QA measurement shown where a multi-field delivery is shown on a phantom, and the dose measurement would be performed in a high dose, a low gradient area of the field. These kind of QA measurements, every clinical physicist is doing on a regular basis. I'm sorry that the labels lost their. The labels are lost here due to a conversion. But what is shown here on the y-axis is the dose ratio measured to the dose ratio of of measured dose to dose predicted by the treatment planning system. And on the x-axis is a typical clinical case. So you see the average spread on this is a few percent. And what is more, there's two things that is worrying here. There's the spread, basically, of these, which is partially due to the dose calculation treatment planning system, but that's what we're trying to verify. But also the difference between three chambers with which these measurements were performed. So there's a systematic effect of chamber type as well. So in an attempt to address these kind of problems, the IAE and the AEPM have created consultancy and task groups or working groups to deal with these issues. And they define basically, in a recent paper that was published in Medical Physics, they define two types of fields: MSR fields, machine-specific reference fields, and PCSR fields, plant class specific reference fields. So what we're trying to do is to bring the calibration conditions closer to measurement conditions or treatment conditions that are used in the clinic. In a static case, the machine-specific reference field is a field that is one of the fields that I showed before, the closest field that you can realize to a 10 by 10 field, giving the limitations of your device. The PCSR field is a class of Stepp and Schul composed fields that realize a uniform dose distribution around the ionization chamber or the detector, so that with the intention to achieve full charge particle equilibrium, so that you can do an accurate measurement. Here are some formula. So the formalism would look like a measurement, a calibration coefficient. This is the same as a KQ factor, and then a factor that takes you from the 10 by 10 field to the MSR, the machine-specific reference field. And the challenge is now to list factors, KQ, MSR factors for different chamber types and for different fields, static field types that can be realized by the device. The formalism goes one step further, and it defines a form of an output factor to go from the MSR field, which is just one standard field on your machine, to any other field that the machine can give you. And you're allowed to measure that output factor, or the protocol will guide you how to use correction factors that are listed in trying to realize this kind of correction factor or this kind of output factor. And you see on this graph that depending on the chamber type or the detector type, that compared to Monte Carlo dose ratios, the output factor corrections can be significant. And there's all sorts of things involved in that, such as relative source size compared to the detector size and other things. Detector type, of course, details of the detector geometry and so on. This is you can consult this material in the summer school book or in the Alfonso paper in medical physics published early this year. This is a summary of what I just said. You have machine-specific reference fields, and the KQ-MSR will take you from either an existing 10 by 10 field or an hypothetical 10 by 10 field to an MSR field. And then the output factor takes you to the clinical condition. Composed fields are using the same formalism. You have a measurement, an absorbed dose calibration coefficient, a KQ factor, which you are using now, and then you have a PCSR, a plant class specific correction factor, that takes into account the composed field and the ionization chamber type that you are using. And also, in this case, the protocol defines an output factor in the same fashion as for static fields. And basically, your IMRT-QA will now be effectively a determination of this output factor, because the calibration of the treatment planning system will be done at the PCSR condition. So you have to realize a PCSR, for example, for a typical treatment such as a head and neck treatment or another type of treatment that is challenging to measure. And this PCSR will describe a dose distribution as uniform around the detector. And once you have made this step here, once you have realized the treatment planning normalization point in the PCSR conditions, the expectation is that this output factor is much more easy to determine. Again, a schematic showing the connection between a 10 by 10 field, a plant class specific reference field, and the clinical field. Recently, we've done some measurements on PCSR corrections. What you expect, of course, is that this PCSR correction should be small, because you're trying to realize perfect charge particle equilibrium conditions. And so the challenge will be to describe the criteria for the establishment of such PCSR for different clinical conditions. But the bottom line is that your protocol will be approximately the same. You will be just having an additional factor that will be measured in a field, the conditions for which will be described in the protocol. So I'm going to stop here. I'm going to give the word to my co-speaker, John Gibbons, who will continue with some clinical, more practical clinical techniques. Thank you.